So this is the beginning of Chapter 2. And Chapter 2 covers diode circuits. And how this chapter focuses on diodes in general, the PN diode that we saw before, is it uses the piecewise linear model that we covered in the previous chapter. That one's too light. Let's try this one. So the piecewise linear model that was covered in last chapter, and we're going to develop circuits that where you have basically an input and an output. So here's the terminals here. And so section 1.1 is the first section where they talk about rectifier circuits. And they go into a generic power supply. And so the first part of a power supply is the transformer. And so I'm just gonna put something like this as my transformer. And so on this side you have your wall socket, your AC voltage source. And then on the outside, this is your output for the of the transformer. So a transformer in general just lowers the voltage. Say if you had 120 volts going in, maybe you'd have 12 volts going out or something like that. And then the diode part of it is right here. We have diode rectification. So rectification, okay, is the process of converting and alternating we'll say AC voltage into one that is limited to one polarity. So we have alternating signal, up, down. And so it has plus polarity, minus polarity. And then through rectification, we're going to convert it to only one polarity. So this is a half wave rectification. And then a full wave would be like this. And so this is full wave. And we'll get into this in a minute. So this is half wave rectification, and this one was full wave. So after the diode rectification, then we have some filter. And the filter is going to try to smooth out this rectifications, something like this, where it's not just dropping down so quickly. And then the last part is some voltage regulator. And a lot of times in a real power supply that I've noticed is this is some IC, integrated circuit chip. And this is resistors and capacitors, this filter, and then a diode rectification, this diode. So this whole thing that I've drawn out here is just a power supply model that you'd have in your computer or laptop or whatever. So like I said, the rectification can be considered half wave, or it can be considered full wave. And section 2.1.1 talks about the half wave. Rectification. And again, we're using the piecewise linear model of a p-n junction diode, and we're assuming the RF for that diode is equal to 0. And so they present in the book a model for that. And so we have our transformer, and so this is our input, and we'll call it VI. And then we have the other part of the transformer, we'll call this VS, that goes into our next stage. And then we have our diode, our p-n junction diode. And then a resistor, which we're representing any generic load. And then our output is taken over the load. And so this is plus minus V out. Okay, and then if you want to calculate what the decrease in voltage will be, you've used this formula, Vn over Vs equals N1 over N2, where this is the number of turns in the input coil, and this is the number of turns in the output coil. And this ratio N1 over N2 is called the turns ratio. And it's going to be characteristic of a particular transformer that you buy. And V input, is usually something like 120 volts RMS at 60 hertz. That's the typical wall socket in the United States. And just so you know that VRMS is equal to V peak to peak divided by 2 times the square root of 2. So we'll need that formula when we work the problems in the back of the book. And the next part is they use their piecewise linear model to predict the output of this circuit. And so I'm just going to redraw it a little bit simpler. We're just going to say this is Vs from here, and then we have our diode, and it has the voltage drop V gamma across it. Then we have our resistor, and then V out plus minus V out. And this is hooked to ground. And if we do KVL around this loop, we're going to have Vs is equal to V gamma minus, oops, I did it again, minus, we'll call this ID IDR, and so our V out, and we could have just skipped this too. This whole, essentially V out's just going to be equal to Vs minus V gamma, okay? I mean, that's really the whole point of it. We could have just, solved this for ID is equal to Vs over V gamma divided by R, and then plugged it back in and got V0. But I mean, from inspection, you can tell that V0 is going to be equal to Vs minus V gamma. And so using this piecewise linear model, our Vs, I'll say this is Vs, and this is this axis is going to be time. It's just our input signal, whatever it is after the transfer. We could just say 12 volts or something. And then our V out, which is across that resistor, is going to look something like this. And this is given for if Vs is greater than V gamma. This is what you're going to get. But if Vs is less than gamma, then V out is equal to 0, because the diode's not conducting at that point. So anytime, and again, we're in this circuit here. We'll redraw it again. This is our V out. It's minus V out. And then we have our power supply Vs. So anytime our Vs, and that's this point right here, is going to be Vs, is less than gamma, then the diode's non-conducting, and so we're not going to have any current. And so if, ID, which is going around here, if ID is equal to 0, then V out, which is equal to ID times R, is going to equal to 0. Now if you put that in there. And so the diode's not conducting, and so you only get a voltage drop when, and so this point right here, this maximum that you see here, is basically going to be Vs minus V gamma at that point, because you always lose the drop over the diode. So now we're going to work example 2.1. And they give you this circuit where the power supply is 24 sine omega t, and they don't tell you what omega is. So, but you don't really need it in there. And then they give you a resistor, that's a 100 ohm resistor. And then they give you a diode, and they tell you that V gamma is equal to 0.6 volts. And then we have another power supply, minus, and they tell you that this is equal to 12 volts. And so you're given this circuit where this is ground here. So this is 0 volts. You're given this thing, and then they ask you some questions. The first question is, determine the peak diode current. Determine the peak diode current. And so that's going to be, if I draw a loop, this is going to be ID. And they want to know what's the largest value of ID. Well, if you look at our power supply, the largest it can ever be would be 24 sine omega t. And if this was equal to 0, say at time equals 0, this is going to be equal to 0. and the sine of, well, actually, that's not true. Not at time equals 0. That would be for a cosine at sine equals 0, 0. So at some later time, because we have a sine wave, the maximum this could be would be when this is equal to 90 degrees, okay, or pi over 2, and that's going to equal 1. And so we'd have 24 volts is the maximum that you could ever see out of the power supply at some later time that's where omega n times t is equal to pi over 2 or 90 degrees. And so we're going to have, if we do KVL at that point, and we just call this 24 at some time later, we're going to get minus 24 plus ID 100, that's R, plus 0.6, that's for the diode, plus 12 equals 0. So that's just KVL. And then we just solve for ID, which is going to be equal to minus, well, we move everything to the other side. So we got plus 24 minus 0.6 minus 12. And we divide that all by 100. I'm just doing algebra here. And so that comes out to 0.114 amps or 114 milliamps. Okay, so that's part one. Determine the peak frequency. And then the next part is they ask you is determine the maximum reverse bias voltage. And so if we drew this here, plus minus, and we have our resistor, and then our diode, and then our power supply, which we said was 12 volts. And so if we're looking at Vs here, then it's going to follow something like this. And so this would be plus 24, and down here would be minus 24. So we'll say this point becomes minus 24. But at the maximum reverse bias, ID is equal to 0. So there's no current flowing. And so there's no voltage drop here. So this has to be minus 24. And then this is still... And then this point would be, we know because this is hooked to ground, this is 12 volts, okay? So then if we look at the reverse bias, we have 12 minus 24, which equals 36 volts. So that's the maximum reverse bias voltage. And then the last question, the last part of that question, is they ask you, number 3, is what is the fraction of the cycle? And they mean the Vs, as it's going up and down, up and down. It's a fraction of the cycle that the diode is conducting. When it's reverse bias, it's non-conducting. There's no current going through it. And so how you have to think about it is like this. We draw out a sine wave. And so this is the input signal, okay? And then at this point right here, you know, because we said this, this is like 24. At this point here and here, where this is Vs minus V gamma, it begins to conduct, and then it conduct, and then at this point, it doesn't conduct anymore. And so conduction happens when, again, if we do KVL, it begins. I mean, it's not happening at this point, but if we look at 24 sine omega t, and this is just KVL, 0.6 and 12. So what I did here was I looked at the power supply, which we knew was 24 sine omega t, and then we have our resistor, and then we have our diode, and then we have our power supply, and this is 12 volts, and then we have ID. So at this point right here, ID is equal to 0. So we have ID equal to 0. So I'm just saying at this point right here, it's just like at the border of conducting and non-conducting. So ID is still 0. Then this is 24, this is plus 0.6, and this is 12. And so you do KVL, it's 24 sine omega t. Actually, it's not 24. So we have 24 sine omega t. There's no drop here because our current's still equal to 0. And then we have the 0.6, and then we have the 12. And so then we just solve for omega t. So we say, well, let's say omega t is equal to 12.6 divided by 24, and then omega t is equal to the inverse sine of 12.6 divided by 24. And then omega t is equal to 31.7 degrees, okay? Because this is an angle, because, the argument of a sine is always an angle. And so I've just done KVL at this point where it's right at the border, where it's not quite conducting, but any more than that, it's going to be conducting. And then just by symmetry, this point's going to be 180 degrees. And so this is just going to be 180 minus 31.7, which equals 148.3. And so the time that it's actually really conducting is the 148.3 minus the 31.7. So that's this area between the two. And then if we divide that by the total time, which is out here is 360 degrees, and times that by 100, we're going to get 32.4%. And so this is the percentage of the time that the diode is actually conducting during a cycle. And so that finishes up example 2.1. Now, the next part, they talk about full wave rectification. So that's the next part. So that's 2.1.2, full wave rectification. So half wave is, we used one diode and we got this half the wave was rectified, and then we kind of threw away everything that was like below here. This was all thrown away. And so full wave, we want to get an output that looks like this. And so they present in the book, the author presents 2 ways to do it. And there may be an infinite number of other ways to do it. I have no idea. But again, we have our transformer, and this is our V input. Again, it's probably like in America, it's going to be a 120 volts RMS. And then our output voltage here. And the thing that they do different is they use what's called a center tap transformer, where this is going to ground. And then we have a plus minus Vs and a plus minus Vs here. And then we're going to use two diodes. So here's one diode, and it's going to a resistor. A resistor that's going in there. And then we have the other diode down here on this end. And it's going to go, it's not going to connect to this line, so we'll just drop it over, and it's just going to connect up there. And then this is going to be our V out plus minus. And like I said, this is a center tapped transformer. And sort of, I kind of thought about this for a while, and to analyze how it works is I kind of broke it up into two sections here, where we have the upper loop, and it's going to ground, okay? So this is plus minus Vs, and then we have our lower diode down here. And this is going to ground. And so we have our diode, and then I kind of looped them together. So I'm just kind of redrawing it so it's just a little bit simpler to kind of conceptualize how it works. And this is our ground here. And then this is our plus minus V out. And so you can see if I draw a input signal, and it's positive. So this is our Vs, and it's positive. So oops, plus minus Vs. Then anytime we're over V gamma, so this is plus minus V gamma, then our diode's going to conduct, and we get a peak. So I'm going to draw this as this is time. So this is our V out. So this is Vs, and this is time on that axis. And so we get a peak, just like we did on the half-wave rectification. And now if we go down here and we draw Vs again, and we have the positive part, well, the positive part's going straight to ground. And then when we're in negative part, so the negative part's going down here, since it's going out the negative one, it gets inverted. So you could sort of think of it like this, is that now we're sort of having it go out the negative, it inverts it. And so now when we're on the negative cycle of the input, we're getting a positive peak. And so then we get something that looks like this. Ooh. And then we go back to this guy, and it's positive again, and then back to that guy where it's inverted, and it's positive again. So so having it this way and having it sort of upside down, it kind of flips the wave cycle that's coming in, the V input. And so now this diode is conducting when that one's off, and this one's conducting when that one's off. And so you get this full wave rectification. So this is the full wave rectification. Full wave rectification. So that's one way where they use the center tap transformer. The other way that they present is using a bridge rectifier. Bridge rectifier. And here I'll draw the transformer again, and then this time they're not using the center tap transformer, and so this is Vs. But now we have the I'm going to draw this out a little bit bigger. It is we have the bridge. And so we have a diode here, and then we have a diode here, and then this is going to go up to another diode, and then we have another diode here. And then we have our load transistor RL right here, and the output is taken across this load, V out. And this point here is at ground. So we're going here. So this is how it's all kind of hooked up together. And so your output is over the load. I mean, it's in between in the bridge. And sort of, I kind of stared at it for a while, trying to figure out what's a good way to think about how this is actually working. And so I'm going to redraw it again. But I'm not going to use, I'm just going to use, say, 5 volts to explain it. Okay? And then we have our bridge. Oops. And this is going to ground. And then we have another diode. And then we have our last diode here. And this is all going back to the power supply. And then we have our load right here, plus minus V out, okay? So at ground we call that 0 volts, and let's say the V gamma is 0.6. So that means over this drop, we've dropped 0.6. So this point here has to be minus 0.6 volts, okay? And if this is minus 0.4, then 0.6, then we go up 5 volts, because this is not at ground. That means this point right here is at 4.4 volts, or basically this whole node here. And then if this is 0.6, then we subtract 4.4, 0.6. So this is 3.8 volts. 3.8 volts. So I just did this DC to make it a little bit easier to understand. So we have 4.4 and 3.8. So this is forwarded bias, but this one is 4.4 and 0 volts. Did I do one of these backwards? Yeah, I did. This one I drew this one backwards actually. So let me fix this, because that would have been totally wrong. This diode should look like this, pointing inward. And actually this one should be pointing outward. I did a bad job here, because when I went to analyze it, all of a sudden it didn't make sense. And so let me erase this. And that diode's correct. Okay, so this one is 4.4 and 0. So this one is reverse bias, so it's non-conducting. So nothing's happening here. So the current's going down here. This one's forward bias. Then we have the voltage drop across V out. And then this one is 0 and minus 6. So this one's forward biased. And so basically the current's following this direction through. And so that's on a positive cycle. So if we sort of simulated it, that's on the positive cycle of the input. Now on the negative cycle of the input, this cycle, then this is just basically on a switch, and all the numbers are just going to be upside down. So this point will become minus 0.06, this point will become the 4.4, and so it'll follow the other path that I've kind of drew out here, where it's whoops, I did it bad here, this whole thing. So on the negative cycle, the current, is going to basically go up here, across the V out, and then up and down, okay? So on each cycle, it's going to use an opposite pair of diodes. And so you can see that basically your V out is going to be your Vs minus 2 V gammas on this. So it's going to have whatever Vs is minus 2 V gammas. So your maximum voltage out is going to be a little bit less than that center tap one, because on the center tap one, each cycle it's going to be equal to V out. It's going to be equal to Vs minus V gamma. This is for the center tap, and this is for the bridge, because each cycle it drops over 2 diodes. Okay, so the last part is they want example 2.2. Example 2.2, and what they want you to do is compare the voltage and turns ratio. Oops, let me write the turns ratio between the full wave rectifier, between the 2 full waves, so the bridge and the center tap. So, and then they say assume V input is equal to 120 volts RMS at 60 hertz, and V out is equal to 9 volts, and V gamma, that's the drop across the diode, is equal to 0.7 volts. So let's make a little table here. We have center, tapped, and then we have the bridge, the full bridge. So that was the 2 full wave rectification things. So I guess they, I don't know if they tell you, but I guess this is V 9 volts peak to peak. And then, so we say, so your V max, okay, that your V out is going to equal to 9 plus V gamma, which is equal to 9 plus 0.7, which is equal to 9.7 volts. Okay. And then your V RMS is going to equal to, now your V peak. We're kind of like going backwards here. So we have our 9 volt output, but we have to take into account we have a V gamma drop, so we're kind of adding that back in. And then our V peak to peak is going to be VR. Actually, the 9 volts, I guess they said it was V peak. So VRMS times the square root of 2 then. So you drop that 2 if it doesn't have it. So VS, so we're kind of back calculating to our VS, is going to equal to 9.7 over the square root of 2, which is equal to 6.867 volts. Okay. And so that's what's coming out of the, remember we had the two parts of the transformer here. And this part was Vs. And so that's what we need to input into Vs. And then for the bridge one, we know we had 9, but we have to do 2 V gammas because there's 2 voltage drops. So that's going to be equal to 10.4. And then if we calculate, oops, kind of doing it sloppy here. Our Vs is going to equal to 10.4 divided by the square root of 2, which is equal to 7.35. So we need a little bit more Vs out of our transformer when we're doing the bridge rectification. And then what's the next part is the turns ratio. So Vi over Vs is equal to N1 over N2. That's what we gave before. So our Vi is going to be 120 over the 6.86 is going to be equal to N1 over N2, which is equal to 17.5. And then on this side, we're going to have Vi is 120 over 7.35. So our turns ratio is going to be 16.3. And so although this is a smaller number, remember that we have it's center tap, so we have basically 2 VS's. And so we're going to need basically twice the number of turns that this guy has. It's not just a slight bit more, it's actually twice because we have VS here and then we have VS here. So there's a lot more VS. Well, I guess that's about it for that question. So that concludes this section.